Good morning, everybody. We are the ESE team from the University of Pisa. I am Emanuele Luzzati.
I am Soufiane Essakhi.
I am Edoardo Simonelli.
So I will start the presentation of our work with a brief summary of the main points. We first present you the final design, and then, of course, we will start back from the beginning, justifying all our assumptions, our optimization strategies, and more importantly, we will explain how we model such a complex and coupled system such as a sloshing rocket. These results have been validated using various different strategies. We conclude the presentation by linking the simulation world and the reality, glimpsing at how we actually manufacture the rocket. This is the 3D model of our final design. As you can see, we chose a deployable wing configuration, and these are the geometrical dimensions. And in this video, you can see the wing deployment phase. Furthermore, those are the performance specification of the final design. But now let's start from the beginning of the concept design phase. We started our journey by thoroughly analyzing the mandatory requirements together with 3 additional requirements we added, namely cost reduction, launch safety, and time. Given that we proved additional constraints which are necessary to close the problem and find the best solution. We provided the proof of this thesis in some additional slides. So, given these deduced constraints, we ended up with 3 possible concepts: fixed wing, conventional rocket, and deployable flexible wing. This is the general approach we followed, firstly, to select the best performing concept, secondly, to optimize it even further. Next, we'll follow a top-down approach and we'll present you the selection results, explain how the optimization problem works. So, those are the results of the optimization of any single concept. And in particular, we can see how the deployable flexible wing design is a good compromise between gliding performance, stability, and it outstands among the others in terms of score points. So this is the selected design with the optimized parameters. And now the optimization strategy. We start the optimization by defining the minimum set of static parameters necessary to completely define the rocket. So we divided the optimization in 3 phases. The first one needed to obtain the best performing concept, the second one to refine the optimization, and the third one to find the control function, angle of attack, and the wing deployment time. Meanwhile, during the second phase, we were able to compare the results obtained from the 2 software and to validate the obtained trajectories. The first step of the optimization is clearly to develop the analytical model for lift, drag, mass, and thrust calculation. Since those are the foundations of the optimization process, we validated them numerically using ANSYS Fluent and analytically using a couple of articles included in the report. As already stated, we followed 2 parallel approaches using 2 different programs, but the main idea stays the same. It has the classical optimal problem definition. Concerning the MATLAB program, we integrated the equation of motion, and then we iterated the trajectory calculation, varying all the parameters until the optimal solution was found. In this case, the control on the angle of attack is activated after the apogee and saturates as 10 degrees. The approach used in the C++ code is slightly different instead, since it used a 1D mesh to formulate and solve a nonlinear problem using pseudo-spectral finite element method. Here we have the results of the optimization, in this case with a single launch tube and the control only after the apogee. You can see the perfect match between the results and especially concerning the angle of attack. On the bottom right, you can find the optimal parameters which were already presented in the section 2.2. Here is the final time in the rocket phase, which is slightly different between the apogee. Next, here we have the results with the telescopic tube, launch tube, which increases at least by 30% the exit velocity at the end tube. The last results are the most interesting one, which because they show the further improvements that can be made, allowing the angle of attack different from 0 just after the end of the water thrust phase. As you can see, there is a substantial increase in the score, mainly due to the fact that the programs holds the attitude of the rocket fixed at -10 degrees and deploys the wing a dozen meters before the apogee. From these plots, you can easily see the 3 phases of the flight, 1, 2, and 3. Now is the moment of the description of the analytical models. For the thrust, we have three contributions. The first one is due to the launch and the launch tube. Then the water thrust phase, modeled by the generalized Bernoulli equation. Eventually, the air pulse, modeled assuming a choke flow and the classical gas dynamic equation for the effective exhaust velocity. Concerning instead the lift drag calculation, we paid particular attention to the wing modeling, since the behavior of the wing during the flight condition is coupled problem between aerodynamic and fiber deformation. From this chunk of code, we can see the aerodynamic coefficients, which are conservative with respect to safety simulations. Then we proceeded quite straightforward, using the classic lifting line theory, evaluating drag and lift, and in the end we accounted for additional drag and lift by the cylinder and the interference between cylinder and wing. The last function is the mass evaluation, which is a pretty straightforward function, and it allowed us to precisely optimize the masses. It predicted a final dry mass of 1.9 kilograms, and we ended up with the real mass of 1.84. And this ends the design phase.
We then proceeded to validate the model. The first problem we faced was the aerodynamics of the flexible wings that we studied with ANSYS and verified through flight test. We then created the thrust and lift graphs and compared the percentage errors of the two models created. We also performed a simulation of the deformation and stress acting on the rocket body to verify that it could withstand the adequate pressure. We conducted a series of 3 flight tests. The first one was without the wing. In fact, despite having reached a rate of apogee at 58 meters, it immediately crashed on the ground in just 8 seconds, covering a negligible distance. The second was a specific test for the wing opening mechanism and allowed to identify and correct some technical problems. The third and final test campaign allowed to reach the best result by covering 467 in 43 seconds, obtaining a score of 159. This test also had the further purpose of validating the simulation carried out, of the results of which proved to be pretty accurate with respect to the real ones, in such a way to allow us to simulate the last launch with a telescopic tube. We wanted to simulate a launch with a telescopic tube because, despite its difficulty of realization, it's allowed to increase the final score by 32%. After the rocket is released, the outer tube remains fixed with the rocket because the inner ring has a bigger area, so it starts sliding along the inner tube. After the outer tube is completely deployed, the rocket itself starts to slide along the outer tube, and then the rocket is released. The launch simulation then led us to obtain an expected flight distance of 680 meters, with a flight time of 65 seconds for a total score of 210. In this slide, we can see graph of position, speed, and acceleration of the simulated launch along the two axes of motion and in modulo. Since the previous trajectory was validated in flight, giving conservative results, we can confidently trust this last trajectory, having just modified the length of the launch tube. And this concludes the part devoted to validation of our design.
Regarding the sloshing geometry, we choose the one in the figure. The external shape fits the aerodynamic and integration requirements, while the internal geometry is a helicoidal with 3 liters of total volume. This configuration is quite interesting from various points of view. For example, during the sudden change of attitude in the transition from climb to glide, this internal helicoidal surface slows down the fluid, which cannot travel in a straight line, as in the case of the hollow tank or with some buffers. Another peculiar feature that was observed after the simulations and experiments regard the fact that longitudinal and pitch excitations of the tank generates a transversal motion of the fluid, and this is beneficial for the pitch stability. We expect that this last feature could be implemented for other applications. A volume of fluid simulation was carried on ANSYS CFX, and we have a video here below where we can see the behavior previously described. In our case, the flexible wings and the control surfaces are able to dump out this roll motion of the fluid. In picture, we see the experimental setup that we used for the experimental data, and we modified the 3D printer and we programmed it to produce oscillations of 1 Hertz which is quite close to the natural frequency that we expected for the sloshing in order to have a relevant sloshing load. The results obtained was fitted with a second-order damped system, and in this way we were able to find the mechanical parameters used in the preliminary design of the control system. Regarding the materials, we see, given the previous hypotheses and constraints that we analyzed, we concluded that the right material choice for the pressure tank was carbon fiber laminated composite. This because we wanted safety and reusability for the rocket. And in the next slides, we can see the manufacturing process, during which, as you can imagine, we had a lot of fun. And here you can see also the electronics, for example. And thank you for your attention.